Recent imaging from the Chinese spacecraft shows a contradiction. The object lost enough mass near the Sun to form a dust tail, yet the images show only a compact cloud with almost no tail at all. The absence is measurable, and it wasn't expected at this stage. By the end of this video, you'll understand why that matters. If this sparks your curiosity, you're welcome to subscribe and share your thoughts. Let's get into it. After its closest approach to the Sun, the object has entered its outbound phase. This is the part of its journey where its brightness naturally begins to fade, its activity slows, and its surrounding material settles. In that respect, what we are seeing now is expected. Most interstellar visitors follow this same arc, a rise in visibility as they heat and a gradual return to obscurity once they move back into the cold. There is nothing visually dramatic about this stage. However, the way information about the object is being shared has shifted. Earlier in its approach, updates were frequent, often accompanied by interpretation and open scientific discussion. Observatories and research teams released findings quickly, sometimes even commenting in near real time. Now, the cadence has slowed. Updates arrive after longer intervals, and when they do, the language is more careful. Statements emphasize the need for verification. Interpretive commentary has become limited. Nothing here suggests dramatic or unstable behavior. In fact, the observations fit the general framework of a cooling, dispersing body moving outward. What has changed is the pacing of certainty. Researchers appear to be taking more time between observation and conclusion, holding off on quick explanations. The tone has shifted from describing what is seen to confirming what is seen before speaking further. This can happen when new measurements do not align cleanly with existing models, or when more data is needed to determine whether a pattern is meaningful. And that is where the focus now rests. The outward path of the object is being tracked with precision, not because the brightness or shape is unusual, but because small changes in motion detected during this phase may hold the key to understanding what is happening next. The first sign of that appears in the new outbound trajectory data. As the object moved farther from the Sun, its outbound path continued to be tracked with high precision. For a while, everything matched the expected model. But then a small, consistent deviation began to appear. It is not dramatic or abrupt. It does not change the visual appearance of the object. Instead, it shows up only in the numbers, a slight directional shift that repeats across independent measurements. When an object releases material unevenly, its motion can be altered. This is a known effect. So the first interpretation considered was outgassing. But for outgassing to create a steady directional push, there must either be a visible source jet or a clear pattern in mass loss. Here, neither is present. The cloud remains compact and no sustained plume has been detected. The lack of a visible mechanism makes the outgassing explanation incomplete. Next, solar radiation pressure was evaluated. In some cases, sunlight can impart measurable force, particularly on objects with very low density or high surface area to mass ratios. However, the estimated composition and density do not match the profile of something that would respond strongly enough for radiation pressure to account for the observed shift. Thermal release of deeper volatiles was also considered, but the water content is extremely low. A slow release of non-water volatiles is still possible, yet the consistency of the deviation suggests something more structured than intermittent venting. This leads to the phrasing now used in analysis: a possible course adjustment, or a non-random directional component is not confirmed but cannot be dismissed. The point is not that the object is steering, rather the data does not fully align with known natural models. So the question now isn't whether the deviation is large. It is not. The question is whether it is intentional, structural, or simply a natural effect we do not yet understand. We will know more soon. A spacecraft is already on its way toward the object. Its launch took place before any of the recent questions or deviations were identified, and its mission profile was set when the object was still understood as a typical interstellar visitor. The goal was simple: to capture direct imaging, gather close-range spectral data, and improve our understanding of objects entering from beyond our solar system. There was no anticipation of unusual behavior at the time. The mission was scheduled because even ordinary interstellar objects are rare, and opportunities to study them up close are limited. Because of that early timing, the spacecraft's approach is not reactive. No course corrections were made in response to new measurements. The trajectory was already aligned to pass near the object, and the instruments on board were prepared to record data across multiple wavelengths, monitor dust environments, and analyze thermal properties. The mission's value has always been tied to proximity. Even the best telescopes can only observe from distance, which means surface texture, structure, and fine-scale material characteristics remain unresolved. What has changed is the interpretive context in which the encounter will occur. The new outbound tracking data has highlighted a question that remote observation alone cannot settle. Direct measurements may help clarify whether the forces shaping the object's motion are uniform, irregular, internal, or external. Not because the mission was designed to answer that question, but because its measurements could overlap with the conditions under which the deviation appears. The significance of the encounter is not that it was planned in response to recent data, but that it arrives at a moment when clarity is needed. The deviation is small, the object is stable, and the interpretation depends on evidence that has not yet arrived. The mission will simply provide the kind of detail that remote observation cannot. Whether the results reinforce familiar models or point to something we have not yet described, the answer will come from what is measured directly. Before the recent outbound observations, several earlier findings had already drawn attention. These did not lead to conclusions, but they formed the backdrop that shaped how the object was studied. The first was the high mass loss without a visible dust tail. Instruments confirmed that material was being shed near the sun, but the typical trailing plume did not develop. The cloud remained compact rather than extending outward into a recognizable tail structure. There was also the sunward jet release pattern. At one point, the direction of the emitted material appeared to face toward the sun instead of away from it. This directional behavior differed from the expected pattern that most solar-heated bodies display under similar conditions.
Spectral measurements indicated a nickel-rich composition relative to iron. While this ratio is not unheard of, it places the object outside the common profiles used to classify most small bodies in our solar system. It is a distinctive signature, noted simply as a point of differentiation. The very low water content was another detail that stood out. Many comet-like objects contain frozen water that sublimates when they approach the sun, yet here the water detected was minimal. This influenced interpretations of its activity and surface chemistry. Additionally, the object followed an ecliptic-aligned trajectory. Interstellar objects can arrive from any orientation, but this path closely matched the plane in which most planets orbit. It is not impossible, but it is statistically unusual. Finally, imagery suggested a lack of widespread dust dispersal. The fine particulate material that typically spreads into space was either absent, limited, or held close to the core, leaving little detectable distribution beyond the immediate vicinity. Each of these details was documented, reviewed, and discussed in the normal scientific process. None provided a definitive conclusion on their own. Individually, each can be explained. Together, they encouraged a more measured approach. The change in tone surrounding the object did not arise from any attempt to withhold information. Instead, it developed because the available data does not fit cleanly within any single established model. Several natural explanations remain possible, but none fully account for all observed behavior at once. When this happens in scientific study, interpretation becomes a careful process. One explanation under consideration is structural variation within the object. If the material is unevenly distributed beneath the surface, internal density differences could produce slight directional influences as it rotates and sheds mass. Another possibility is compositional layering, where pockets of different minerals or volatiles release at different rates, producing subtle forces that are difficult to detect visually. Thermal processes are also being evaluated, including slow-release sublimation or delayed heating effects that could generate steady, low-level motion without an obvious plume. Each of these models can explain part of the behavior, but none of them explain all of it. The deviation is small, but it is consistent, and consistency suggests an underlying mechanism rather than chance. Because of this, researchers are choosing to interpret the data carefully rather than select one explanation prematurely. This is not unusual. In fields where measurements are precise but incomplete, tone shifts naturally from broad discussion to focused evaluation. The goal is not to avoid questions. It is to avoid presenting answers that are not yet well supported. The caution is methodological, not protective. The upcoming close encounter is valuable for this reason. It will not provide instant certainty, nor is it expected to produce dramatic revelations. What it will offer is the kind of direct measurement that can distinguish between structural, compositional, and thermal explanations. The importance of the encounter lies in its ability to narrow the possibilities, not to confirm any predetermined conclusion. The close encounter provides an opportunity to obtain measurements that are not possible at long observational distances. Telescopes can detect brightness changes, broad compositional signatures, and motion across space, but they cannot resolve small-scale surface features or localized variations in temperature and density. The spacecraft's instruments are designed to address this gap directly. High-resolution imaging will document the object's surface texture and overall morphology. This includes whether the exterior is smooth, fractured, layered, or granular. Surface structure can indicate how the object formed and how it has changed over time. Variations in reflectivity can also be mapped at close range, offering a clearer sense of material distribution across different regions. Thermal mapping will record heat retention and loss rates. These measurements can show whether certain areas warm or cool more quickly than others. Uneven thermal behavior may correspond to compositional differences below the surface or to internal voids and fractures. The pattern of heat distribution cannot be interpreted accurately from a distance. Direct readings are required. Spectrometric analysis at close range will provide more precise compositional data. While remote spectroscopy identifies broad elements and minerals, proximity allows detection of trace components that may be masked at long distances. This can clarify the presence and distribution of metals, silicates, carbon compounds, and any remaining volatiles. Dust and particle environment sensors will monitor the space around the object. If small amounts of material are being released, these instruments can detect and characterize the particles even if no plume or tail is visible. The direction, size distribution, and velocity of particles can indicate whether mass loss is uniform or localized. None of these measurements provide answers on their own. Rather, they supply discrete data points that can be compared against existing models and simulations to determine which explanations remain viable. These measurements will help refine the current models. The outbound deviation remains small, steady, and unresolved. It does not point clearly toward a single explanation, and it does not indicate instability. It simply remains present in the data, repeating consistently enough to warrant attention. The object continues to fade as expected in its outbound phase, and the measurements collected so far provide a framework, but not a conclusion. The upcoming close encounter will not provide instant answers. It will provide measurements, surface imaging, thermal readings, compositional sampling, and particle environment data. These are the kinds of observations that cannot be gathered from long distances. If the deviation is tied to structural variations within the object, such as density gradients or layered material, close imaging may help identify that. If thermal release or slow volatile loss plays a role, localized heating patterns may clarify how that occurs. If the explanation lies in a combination of factors, the data may show how those elements interact. It is also possible that the new data will introduce additional complexity rather than simplifying the interpretation. In that case, the result is not confusion, but refinement. Scientific understanding develops by comparing new information to existing models and adjusting those models where necessary. The significance of the encounter is not in confirming one answer, but in narrowing or expanding the range of plausible explanations based on direct measurement. At this stage, the most accurate position is observation. The situation is steady, the object is stable, and the interpretation depends on evidence that has not yet arrived. The upcoming data will speak for itself. If you have thoughts on what may be driving the deviation, feel free to share them in the comments. And if you'd like to follow the analysis as new information becomes available, you're welcome to subscribe. Thank you for watching, and I'll see you in the next video.